Okay, so so we're ready to now relate the Riemann curvature tensor to um, the the what we call the de Rham curvature. So what we computed was that kappa. Oh, so we had this. We had two definitions, right? We had this Riemann guy, um, and given two derivations, it was defined to be the commutator of these. So how much the covariant derivatives commute. And then we had this guy, which was the second exterior power, and this thing we viewed as a map to from E to omega 2 tensored with E. So this is kind of the more algebraic version here. And so we saw that both of these were related to the so-called Faraday tensor. So here, if we had our locally, if we write our connection as d plus omega, where omega is equal to ai dxi, and so these guys are a local set of so x1, xn local parameters for s. Okay, then what we saw is that these two guys are related by the following relation to the Faraday tensor. So we had this the computation, the local computation that we did was that so let's say that di is d dxi I. So then we had this guy was equal to this Faraday guy, the Faraday tensor, and then we also had the curvature, right? So that omega was equal to Fij dxi dxj here. So this was this curvature guy, and remember that that this guy here was of some vector, so in some trivialization, was given by omega gamma beta tensor E gamma. And then Einstein's summation is implied here. So this is the total collection of these guys. So this is kind of the matrix of curvature, or the matrix of curvature two forms here, and this Fij was given by the following formula. So using this guy here and these potentials, we had this formula dj ai plus ai aj. So we saw this from two separate computations. So in particular, this tells us that vanishing of this will make both of these vanish. Will make both these curvatures vanish. So in particular, so omega, this is also equal to this matrix of these guys. And so it's kind of funny. So these are written in the spatial coordinates, and then these are written, this is these Greek things are in the bundle coordinates. So the Roman ones are the spatial, and the Greek are in the vector coordinates. Okay, so this is what we have, and what can we conclude? So the conclusion is that so that de Rham flat is equal to Riemannian flat is equal to that these all the Fij's being 0. Okay, and so like you can specify flatness for these two things. Okay, and then in algebra, in the algebraic geometry, or when we're working with algebraic schemes, we also have this notion. To Rom flat is equal to Riemannian flat is this. So we have flat morphisms. So sometimes we'll call if any of the following conditions, if K or equivalently R is 0 for a connection on a line bundle or a vector bundle, we say that the vector bundle with connection is flat or integrable. So this is a module with integrable connection, and then due to what we said about the de Rham, so that this is really this squared, we get a de Rham complex. Okay, so that's all I wanted to say about this for now. I'm going to stop the video.